Just to introduce myself again, I'm Aaron. And I guess the reason I'm here is I did my graduate work with Michael Fee, who does a lot of extracellular electrophysiology. So I spent a lot of time doing recording single units in awake singing birds using a motorized microdrive. And then since I got here, I'm in the Dice-Roth lab, and I did a little bit of work with tetrodes in mice, but now I'm doing calcium imaging. So I'll try to hit on what I think are some of the key points, and then if any of you are actually trying to do this, I can field questions on some of the more obscure points. All right. So conceptually, as Alex had alluded to, it's really simple. We're going to stick a wire in the brain and measure a voltage as the animal runs around. But when you go to actually do this, you have to make many more decisions than just, what kind of animal I'm going to stick the wire into, in what behavior. So I sort of tried my best to break down all the different components you're going to need into categories, which are here. And I've made some slides about some of them and just have some bullet points on others. And I'll try to go through it quickly and then take questions. So I guess I'll spend the most time on this one. So this is the most important decision you're going to make if you try to do extracellular electrophysiology, and that is what electrode are you going to use? Because this is going to determine what you actually will measure. And so there's sort of two principles that should guide you. The primary one should be, what do I need to answer my question? And so if you're looking for LFP versus multi-unit, you want to get the general sense for activity in an area versus single unit, that's going to really be the determining factor. And then a secondary question is, how much time, money, and effort do you want to put into this experiment? Because obviously everyone would like single units if they could have them. So if you wanted to spend the time, you can make that happen. All right. So before we go over different types of electrodes that are already out there, I thought I'd cover sort of two properties of electrodes that I think get discussed a lot, and there actually is some confusion about in the field. And those are tip geometry and impedance. So essentially, you're going to stick a wire into the brain, and it's going to be insulated except for the end, and the end is going to have some shape. And that shape is actually really important in determining what you're actually going to measure. So here's a couple of electron micrographs of different electrode types. So this is an SEM of a tetrode that Tom actually took at graduate school. And what it shows here is the tip. So a tetrode's 4 microwires twisted together and then cut. And these are the ends of the 4 wires. And each end is about 12 microns across. And here's an electron micrograph of what's called a sharp microelectrode, which is essentially a piece of quartz with, this is what this one is. It's a piece of quartz with a little bit of platinum iridium down the middle, pulled to a point, and then sharpened using an etching technique. And this is the tip of that electrode. And that's about 4 or 5 microns across. So that's going to really determine, as you can imagine, what you're going to see at the end of your electrode, quote unquote. So we have a very small tip. It's going to be sensing the electric field in a very small area, and it's going to be more likely to sense the electric field produced by just one neuron. Whereas if you have a very large tip, you can imagine you're going to that the electric field that's influencing that tip is likely going to be affected by many neurons. And then another thing to think about, that comes up in electrophysiology a lot is you're moving these electrodes sometimes, and you can move these electrodes pretty long distances sometimes and still be recording the same cell, or sometimes it's just you have a cell and then you go another 10 microns and it's gone. That's sort of because this picture is oversimplified. So these cells have complex morphologies, and the position of this electrode relative to some dendrite. So imagine you had a dendrite running vertically here. You might record from that neuron for a large distance. So it's more complicated than this simple picture I drew up in 5 minutes, but it kind of gives you a sense. So now you're like, okay, well, if I want to record single units, I should just choose the smallest tip I can, and that will be the one that most likely gets me a single unit. But there's this other property of electrodes that sort of is the reason you don't just make smaller and smaller tips, which is impedance. So for the people out there who are not, electrical engineers, what is impedance? I think the easiest way to think about impedance is, well, I'm going to assume that everyone knows what resistance is, because that's a simpler concept. So it's basically the resistance of something at a particular frequency. So it's like the resistance at 1 kilohertz, or the resistance at, it's a resistance, but you need to tell me the frequency before I can tell you the resistance, essentially. And what there is to know, as like a big picture, is the smaller the surface area of the tip of your electrode, the bigger the impedance. And the other thing you need to know is that big impedances are bad for a couple of reasons. So I'm going to go through 2 of them. The first is thermal noise. So there's an equation which tells you what your RMS voltage noise is going to be as a function of your impedance. And it's 4 times Boltzmann constant times temperature times the bandwidth you're interested in times the resistance of that, or the impedance of that electrode. And so it's going to go up the higher impedance you're at. So you're basically going to get more noise the higher the impedance is. So, that's bad, but at 10 megaohms, which is about as high as impedance that you're going to bump into, it's only 40 microvolts noise. So this is sort of defines your noise floor, but it's not the big problem with impedance. The big problem is that high impedance electrodes makes your whole experiment sensitive to other sources of noise that are larger and you really want to avoid. So namely capacitive coupling, which is, I've got some machine over here that is pumping water through some tubes. That's producing an electric field. If I have a high impedance electrode, it's going to be more sensitive to this sort of surrounding equipment, despite shielding. There's also 2 other types of noise that it becomes more sensitive to, which are audiophonic noise and triboelectric noise. So I'll just touch on those really briefly. But first, let's talk about capacitive coupling noise. How long? It's already been 7 minutes. Okay, so let's see. This is like the basic circuit diagram of an extracellular electrophysiology experiment. We have we're in the brain somewhere, and so we're measuring some electric field or voltage produced by neurons, or 1 neuron. That's what this indicates. And now we're going to measure that with some electrode which has an impedance, and that's going to go into an amplifier and give us an output. And we want V output to be neuron, right? That would be the ideal situation. And so if this was the only circuit elements affecting our measurement, that's exactly what we'd get, because this amplifier has an input impedance of basically infinity. Like the ideal amplifier has an input impedance of infinity, so let's consider this infinity. And this is something smaller than infinity. So you can sort of think of, you've got a voltage divider between your amplifier and your neuron, and this voltage will be equal to basically Z electrode over Z plus R. And if R is infinity, this will just equal V neuron. So V amplified will be V neuron, so V output will be V neuron, and we're done. So the problem comes in when you start thinking about the non-ideal environment. So here's this, pump or whatever equipment you have in your room that's generating some noise. Even though it's separated by shielding and air, you can measure some very large capacitive coupling, which is an impedance between that noise source and your electrode. And the extent to which this noise source is going to affect V amplified, which is actually what you're measuring, is basically going to be given by this equation, which is, it's going to be V noise minus V neuron times, and this is the key ratio, V electrode divided by the sum of V electrode and Z electrode and Z coupled. So basically, the bigger ZE is, the bigger this term's going to be, and the more your electrode's going to be sensitive to coupling. Does that make sense to everyone? So essentially, I guess the take-home picture is always choose the electrode with the lowest impedance that will give you the type of signal you need. So let's just go over some ballparks. You want to make a nice single unit recording without doing any sorting. You just have like a really clean signal, maybe like 10 millivolt signal. You probably want to use sharp microelectrodes, which are going to have an impedance between 1 and 10 megohm, which means your setup's going to be pretty sensitive to like how you shielded it, how short that. So one thing to touch upon is, let's say you are trying to get single units, and this is a high impedance section of your circuit. So this is sort of from the electrode to your first amplifier. What you want to do is make that as short as you can make it and as rigid as you can make it. If this is some big long wire going through your environment, you're going to have to do more shielding. You're going to have to, it's going to be more sensitive to movement. So I didn't touch upon these two other things I said I would, which is audiophonic noise and triboelectric noise. So in addition to sort of some machine generating noise, when your cable moves, it generates two types of noise. So audiophonic noise is sort of like when these materials bend, there could be some piezo effects, which means basically turning strain into a current or a voltage. And that, if you have a high impedance electrode, those tiny little generated piezo currents can generate voltage swings that actually interfere with your measurement. And the second is triboelectric noise, which is basically when those cables move, the conductor slides relative to the insulator. All right, and it's kind of like when you rub a balloon on your hair and you generate static electricity. That rubbing of the conductor against the insulator can generate some charge, and that charge can produce electric fields, which if you're in a high impedance environment are actually big enough to affect your measurement. So essentially, you can never shield away these two types of noise. Those are like intrinsic to the cable that's connecting your electrode to the amplifier. So what you want to do is keep that very short and very rigid so that there's not a lot of movement, which is what induces these types of noise. So essentially, high impedance just yields lots of problems. So you want to avoid it if you don't need it. All right, so as I was saying, so here's sort of your sort of spectrum of choices. Sharp microelectrodes, if you want really nice single units, that's pretty much your only choice unless you're dealing with a system that has giant, like giant squid axons or huge neurons. The other way to get single units is to get slightly less clean signals, but then do some spike sorting. So tetrodes are one way to go. Those are going to have an impedance 400 kiloohms. Would you agree with that?
For the tetrodes, I guess the measurement that you're giving of the geometry is the cross-sectional area.
I'm giving the diameter. Sorry, I didn't compute areas. Sharp electrode, that's also the diameter. So you would want to convert those into areas, which I didn't do. But you could multiply by pi r squared.
I don't mean to.
Yeah, no, go ahead.
Much, but one thing I didn't get.
I would like it to be interactive, so fire away.
One thing I didn't get with the tip geometry. Are you saying that the only effect of a bigger tip geometry is that you're literally like spreading out your recording surface? Like if you were to draw on this diagram you had of like the little tip versus the big tip, the radius over which you can like expect to get a signal of a certain magnitude or something like that. Are you saying like that bubble around the electrode would be exactly equal radius on the small guy and the big guy?
It's just the surface that's making the measurement. So literally it's the surface that's making the measurement. But it's the field that's impinging on that surface. In terms of how big an electric field a neuron generates, how far that field is. So if you had one neuron and nothing else around, that neuron could be very far from your electrode and you'd still be able to see that field generated by that neuron because there's nothing else, there's nothing grounding it in between you and the neuron. So
it just seems like, I definitely don't know the physics and we probably shouldn't get into it now, but like it seems like if you have a really small electrode tip and there's one neuron near it, that neuron signal is occupying 100% of the
right. That signal's dominating.
Whereas it's only occupying maybe 1% of the bigger electrode's tip. It seems like it would contribute less not just because it's.
So you could sort of
Yeah,
imagine.
But
Go
it
ahead.
would again depend on the area, depend on how packly the neurons are,
Right.
and also basically the shape of the particular electrode site.
Yeah.
Right. The shape of the electrode is going to determine exactly where you're sampling the field. The extent to which a given neuron will impact the field at this point depends on the density of other neurons, the morphology of that neuron. So, in one environment, this electrode might be able to see neurons this far away. If the neurons were very sparse and there wasn't all that much neuropil, then they could see quite far away. But if you're in an area where there's tons of neurons and there's dendrites from various neurons intertwining, then to get a single unit recording, you would need a smaller tip that was very close to that particular dendrite. Does that give you some intuition?
Can I
Yeah, go ahead.
Because I think it's a perfect place. So the one caveat with using like really small, sharp electrodes is, especially in behaving animals, the electrodes move.
Yeah.
And as they move, they might impale the cell and basically kill the cell that you are recording. So I think that's like one of the biggest things. Because if the tip is relatively bigger, even if the electrode moves, you can still perhaps record it from other sites. But with really sharp electrodes, I think it's safe.
Yeah, so, and that also could depend on how rigid your electrode is and how it's held outside of the brain. So if you have it held very rigidly, then when the brain moves, it's going to move relative to the brain, which might impale the cell. Yeah.
The other phenomenon that hasn't been mentioned yet is sort of spatial averaging of the field. So if you've got an electrode
I
with
was
a large
trying
area,
to make that point here, but maybe
Yeah.
I didn't make it.
Well, you were saying like the size of the voltage generated will be the same whether you have a large or a small electrode, and I feel like that's accurate. But if the configuration of the electric field coming from that cell is such that when you average over a larger area, it could cancel out.
Right. This is going to average the voltage at all of these locations,
Right.
and just make one measurement. So this cell could be impinging very strongly on this corner, and this cell impinging very strongly here, but what you net record is going to be an average over that entire area. So this would never, if you were dealing with neurons this size and in this density, this type of electrode would never give you a single unit recording. Yeah.
There's another point of having an electrode with a large cross-sectional area, silicon probe with a large cross-sectional area, and that as you put it down into the brain, you destroy the
Right.
neurons, the connect.
Yeah, I wanted to make that
connections.
exact
You're
point.
getting to that.
Well, I was going to say, so this sort of design, say you wanted to record from that location, by the time your electrode's there, you're going to have, it's on the side of the electrode, so by the time you've lowered it, it's going to have put a slice through the brain. So you're going to be recording from an area where many of those processes may have been damaged. Whereas with a sharp, where you're recording from the very tip, I don't actually have a picture of a sharp here, but you'll have done less damage, but you might have some jostle. So if you get very close to a cell and then you move, you're going to kill the cell, and then your recording might be shorter.
I'm just going to quickly jump in.
Yeah. No,
It's-
this is good. This is
Yeah,
what it's for, right?
true. You're definitely like inserting something into brain. Like we can't argue that. But the tissue damage is really minimal with simple probes. If there are certain tricks, so you have to go really, really slowly over time. You can, in fact, let's say that you can start recording from a neuron at site, 16. If you are, like really, site 1, if you go really slowly, you can start to see it in upper sites, and you can see it reliably and stably. So, and in fact, sometimes one caveat is if you don't put a dye or something on a silicon probe, you might not even recover where you recorded from.
I don't know if that's an exact measure that you're not doing.
But-
Like you go very
No,
slowly
I'm-
and you still see it, but it may be that happens to be a neuron that's pretty far away and the dendrite's just passing by your probe.
We can
Yeah,
discuss
yeah.
on this like hours. Yes,
Yeah,
there
yeah.
is that possibility, but I
Well,
think there's also.
It's hard to assess the amount of damage that you
What's the average sort of geometry of the silicon probe? What's its width?
I haven't worked with silicon probes. Sounds like she might know the answer.
Yeah, I have some, but do you?
We're just spitballing. Like, is it on the order of 500 microns in diameter?
You mean like the area? So
The long, or let's say the long, yeah. The width of it.
So very close to the tip, so the whole thing is optical shank.
Right.
It can be like 12 micron,
Okay.
20 micron. If you go like further up, the bulk of the place, it
Yeah.
gets kind of like bigger. But often those are the part that you don't really insert into the brain.
Right. But so like, what's the bigger, where it says sort of optical fiber on that thing, what would be the width across there? Like 300 microns, 500 microns,
Less
a
than
millimeter?
that, less than that. Maybe 100, maybe 200 micron. The thing is though, you have plenty of designs, plenty of
Different options.
configurations, exactly. We can discuss it a little bit later.
Okay.
I can,
Go ahead.
I can give a quick rule of thumb, which I learned from Michael Stryker and Chris Neal, which is that the width in the mouse brain, they study the visual cortex, should be less than 80 microns. I
Okay.
don't know if, I'd like to know whether this is a good measure. If it's larger than 80 microns, they consider this to be too damaging to get
Okay.
reporting
That seems
from the
reasonable.
mouse. And the thickness is typically 15 to 30 microns.
On the thin width.
I don't know if I'd go for a rule of thumb like that. You know, I think if you do a
Well,
control
that's
and
why
say
I'd
I
like
put
to-
in I put in
people
a
have
larger
other,
one, and my control
numbers.
animal doesn't show any difference in the behavior. You know,
A
it's
lot
hard.
of-
It seems like an arbitrary number to me.
One
Talk to Michael
variable-
Stryker about it.
Sorry. One variable you haven't mentioned, or you probably did, is what structure you want to record from. So if you have a structure where neurons are not lined up and there aren't laminae and so forth, so it's a lot easier to record units, say, in dentate or in CA1 campus than it is in neocortex
Right.
because of that.
Right. So that might affect like what type of drive you choose.
Yeah.
So I think we almost. So then beyond tetrodes and silicon probes, I'm almost at the 20-minute mark. So I'm gonna try and wrap up. There are. You could just record multi-unit with just a wire cut off. You know, just stick it in the brain. Or LFP. You can record LFP with like a 1 millimeter metal disc, which essentially has no impedance. And so you don't need any preamplifier, any head stage. You just run a wire from this disc that's on the brain to an amplifier, and you're done. So you know, there's when you're dealing with a low impedance setup, you don't have to worry about noise or like the exact construction of your drive in nearly the same way. So then, I'm gonna leave that. Right. So sort of getting to your point. Depending on what area you're going to record from, you may need to choose a different drive type. So there's a lot to cover here. There's been millions, well, not millions, but many, many drive designs. But I think some of the key decisions are, do you need your electrodes to move, and how stable do you need them to be? So if you're recording from an area where neurons are sparse, and just plunking a neuron into the brain at the appropriate depth is unlikely to give you a nice recording, you need to really move it around to find a cell or find a nice multi-unit area. You want a drive that is either manually or motorized, movable. Whereas if you're recording from an area where cells are dense, you could just plunk a wire in, cement it into place, and then when you go to record from it, there's like a decent probability that that particular wire will have a nice recording. You know what, I'm going to not go into all the different designs. There's motorized designs, there's manual designs, there's different designs for different size animals, and there are designs that are going to give you either longer or shorter recordings because of the stability of their placement. So all of those things affect how you might decide. And if you have questions about connectorizing, cable management, amplification, dealing with noise, or like surgeries, maybe we could talk about it at the end or something like that.
That's true. I think some of these guys might be talking about some of those aspects too.
Great.
So they might.
All right, I'll leave it at that. Thank you guys.
All right.